Unit 5, Geological Investigations for Civil Engineering Structures. In this unit, we see about remote sensing technique and air pollution, air photos, satellites images, geological conditions necessary for construction dams, tunnels, road cuttings, landslides, then causes and prevention of sea erosion and coastal protection. First, we know what is remote sensing. Remote sensing is the process of collecting data about objects or landslide features without coming into direct physical contact with them. Most remote sensing is performed for aircraft or satellites using instruments which measure electromagnetic radiation that is reflected or emitted from the terrain. In other words, remote sensing is the detection and measurement of electromagnetic energy emanating from distant objects made of various materials. This is done so that we can identify and categorize these objects by class or type, substance, and spectral distribution. Remote sensing can be of acquiring, that is, technology employed like satellite, aircrafts like that, and processing, that means converting raw data into images. And finally, interpreting. Interpreting means giving meaning to the process data. How to acquire digital data? Scan photographs or purchase digital data from agencies such as NASA, USGS, DLM, Forest Service, or a private company such as Space Imaging. The data used to come on high density digital tapes that had to be read by a tape drive, usually one band per tape. Now, most data is available on CDs and memory card like that. Spectral resolution. In general, resolution can be defined as the area underground represented by each pixel in the image. That is, 20 meters on the ground or represented by 20 meter pixel of spot data. If you recall, the smallest units in raster data are known as cells or pixels. High resolution refers to raster with small cell dimensions. High resolution means lot of details and lot of cells. Raster GIS. Rasterized data divides the entire study area into a regular grid cells in a specific sequence. The conventional sequence is row from the top left corner. Each cell contains a single value and is space filling. Cell values, each pixel or cell is assumed to have only one value. This is often inaccurate because the boundary of two soil types or vegetation and concrete may run across the middle of a pixel. This is called as a mixed pixel. Vector GIS. This model uses discrete line segments or points to identify locations. Discrete objects are formed by connecting line segments. Vector objects do not necessarily fill space. Not all locations in space need to be referenced in the model. Raster GIS. You can either create your own raster data, rasterize vector data, or access digital data in raster format that has already been archived. The latter is the most common way to acquire and use raster data. False color composite. One thing that you may have noticed on the images is that the vegetation comes out in red. That is what we refer to as a false color composite, where we have combined bands 4 near IR, 3 red, and 2 green. Healthy vegetation has a high reflectance in the near IR region. How could you use remote sensing in civil engineering? Erosion protection, that is stream ban and shoreline erosion management. transportation modeling, dam and reservoir location and planning, geomorphology, that means channel and watershed characterization, characterizing soil dynamics, geotechnical and environmental engineers, earthquake engineering, construction engineering, agricultural engineering, geological conditions for the constructions of dam. The geology on a large dam construction project, the engineering geologist is concerned with the geology of the dam site, including the foundation for the dam itself and the sites for other structures such as spillway, diversion tunnel, and outlet works. Questions that need an answer include whether the dam foundation has sufficient strength and durability to support the type of dam proposed, whether the foundation is watertight, and if not, how much grouting will be required, and whether the spillway will acquire concrete lining. The geology of the area to be occupied by the reservoir once the dam is completed. Questions often asked here include whether the storage area is watertight or there are areas of cavernous limestone which might lead to the dam not retaining water, and whether landslides into the reservoir are possible, which might cause a wave of water to be pushed over the top of the dam. Finding sources of these construction materials which will be needed to build the dam. The primary purpose of geological site investigations for the dam is provide the information that dam designers require in order to design a safe dam structure and to be able to estimate with reasonable accuracy how much the dam is going to cost. The aim of the dam designers is to build the dam for the lowest cost consistent with currently accepted standards of safety. The engineering geologist must be able to answer the following questions. First, what is the depth of overburden that must be removed to reach an acceptable foundation for the dam wall? Next, what are the rock types which make up the foundation and to what extent are they affected by surface weathering? And the another question, what are the engineering properties of the foundation rock types? Important properties like strength, deformability, durability, compression, like that. And the another question, what is the geological structure of the foundation? That is, where it is the jointing, faulting, and folding of the rock strata. A full description of the defect pattern in the rock most should include orientation, phasing, extent or persistence, and aperture or openness. And then how permeable is the rock foundation? That means what extent or the rock defects such as joints, faults, and bedding open. Next question, where can adequate supplies of construction materials such as clay, sand, gravel, and rock fill be obtained preferably as close as possible to the dam site? Will the rock that must be excavated to provide a spillway for the dam be acceptable for use as rock fill in the construction of the dam embankment? Will the spillway require concrete lining and an energy dissipation structure and its downstream end? Or is the spillway rock sufficiently erosion resistant that these can be omitted? In order to able answer the above questions, the dam site must be explored by an experienced engineering geologist. Methods commonly used to explore sites for construction projects are geological mapping of surface rock outcrops, geophysical surveys, seismic refraction is often used to determine depth of overburden, excavation of trenches and pits using bulldozers, backhoes, etc. Diamond core drilling, as usually carried out, this method recovers an undisturbed cylindrical sample about 50 mm in diameter from depth of a few meters to hundreds of meters if necessary. Other types of drilling which recover disturbed samples may also be used in some circumstances. What are the types of dams available? Like gravity dam, buttress dam, multiple arch dam, thick arch dam, thin arch dam, rock fill dam, hydraulic fill dam, earthen embankment, and composite dam. First thing, gravity dam. In a dam, this is the upstream side where the water stored in huge quantity. That side is called an upstream side. And this portion is downstream side. This is the downstream phase, and this side is the upstream phase. And this is top portion is called as crust, and the bottom portion is known as base. In front of the downstream side is known as toe, and this side is called as heel. In a gravity dam, we need hard rock surface near the subsurface. Depth of soft material above the rock should not exceed 7 to 10 meters, thereby avoiding excavation. Materials for concrete, that is aggregate, stone, sand, should be easily available within 5 to 10 miles. Gravity dams are suited when the length of the crust is 5 times or more than the height of the dam. Next, buttress dam. This is the buttress dam. This is the cross section of the buttress dam, and this one is the plan view of the buttress dam. The buttress dam is suitable where the rock is capable of bearing pressures of 2 to 3 megapascal. Buttress dam require between a half and 2/3 of the concrete required for a gravity section, hence making it more economical for dams over 14 meters. Additional skilled labor is required to create the framework. Threat of deterioration of concrete from the impounded water is more likely than from a thick gravity section. There is also an elimination of a good deal of uplift pressure. The pressure resulting from the water in the reservoir and possibly of water from the hillside rocks gaining access through or under any groove cutting and exerting upwards underneath the moss concrete dam. Next, multiple arch dam. This is the example of multiple arch dam. Multiple arch concrete dam is a variety of buttress dam. The chief geological criterion is that the rock must be absolutely reliable to bear 2 to 3 megapascal or move without any appreciable settlement is less than 8 mm. There is some saving in concrete compared with buttress dams. In respect of uplift, corrosion, and economy, the two types are very similar. That is thick arch dam. Another one is thin arch dam. Thick arch dam can be built where the crust chord height ratio is between 3 and 5. The chief geological criterion is that the rock must be absolutely reliable to bear 3.5 megapascal or more without any appreciable settlement. A substantial saving in material compared with that of gravity dams. Thick arch dams are difficult to design on paper but are well determined from trials on models. Thin arch dam. Thin arch dams require valleys to have a crest shot height ratio of under 3 with a radius of under 150 meters. The pressure exerted on the valley side is between 5.5 to 8 megapascal, where there is a vertical radius of curvature as well as horizontal. This is known as a dome type, used where cement is expensive and labor is cheap. Next, rock-fill dam. There is the examples of rock-fill dam. This is the crest portion, and here it is the wall. This is the level of reservoir, the upstream side, and this one is the downstream side. Here we filling full of rocks. Uncertain or variable foundation, which is unreliable for sustaining the pressure necessary for any form of concrete dam. Suitable rock in the vicinity, which is odd and will stand up to the variations better. Accessibility of the site and the width of the valley is suitable for manipulation of heavy earth moving machinery, caterpillar scrappers, sheep foot rollers, and large bulldozers. Next is hydraulic fill dam, suitable in valleys of soft material and are constructed by pumping soft material duly consolidated up to moderated heights up to 30 meters. Next, earthen embankment or earthen dam. Near the site, there must be clay to fill the trench and embanking material capable of standing safely without slipping to hold up a clay core. An advantage of earthen embankments is the troubles due to deterioration of the structure by petty waters of low pH do not rise. This is an earthen embankment. Next, composite dam. Not only can different types of dam can be built in the same valley, but the same dam can be of different types owing to the varying geological and topographical features on the dam site. Many buttress dams also join up with gravity mass concrete dam at their hanches at the sides of the valley and gain at the center have a mass concrete gravity dam to form a suitable overflow or spillway. General factors to be considered while selecting a site for dam. First thing, topographical condition. A place which is most suited, that is, it would be a narrow gauge or a steep valley with enough catchment area. Next, technical condition. Site should be sound as possible, that is, impermeable, strong, and stable base and subbase layers. Uniform base course for proper distributing of loading. Constructional condition. Constructional condition should not be far away from the raw material site. Spillway material should suited for the embankment fill. Economical condition. Economical condition should be realistic and justified in terms of irrigation and power generation. Economical condition should be flood averting. It also should be multi-purpose with recreation providedness. General factors for the investigation of dam site. First one, geology of area. Detailed investigation on the geological mapping covering the geological site of reservoir. Geology of site, that is lithology and structure. Structure is considered in two categories, dip and strike and fault. Lithology, slope of the valley should be comfortable. Composition and texture of rocks should be in proper. Classes of the rocks should be revealed, that is igneous, metamorphic, and sedimentary rock. Rock strata has to be revived. Structure, dip and strike. Dip should have proper bedding angle load. Beds must align in a way that should not parallel to the loading direction. Fault. Provision must take against the fault plane with diverse strata on either side of fault. Dams found on the beds traversed by fault planes are more liable to shocks and vibrations. Fold. Dams on the axis of the fold lead to collapse. Synclinal beds dams over such leads to decay on the upstream limb. Factors due to engineering properties of rocks. First thing, strength parameter. Strength parameter means resistance to working load of the dam is in the hands of strength of the beds. Hardness and toughness of the surface is important to avoid seepage. Permeability, drain condition will allow the water to flow during overpressure. This flow maintains the equilibrium pressure in and out. Undrained condition acts reverse leads to increase in pressure over the beds and dams. Seepage on weaker section of soil leads to settlement of the soil. So this class we see what is the conditions for construction a dam. In following the next classes, we see what is the geological conditions for tunneling. Thank you.